So let's have a look at these two familiar concepts related to two variable functions, and as they relate with calculus. The first one is the one I've just mentioned, and that is the one related to level curves. If I have a level curve, what I really have is an implicit relation between the two independent variables, x and y. Now we know that that an equation like that will have a graph that is a curve, but it's a curve that may look like this. So it's a curve that may not be a function. So sometimes it is, but not always. A function here, of course, I mean a function of, as y being a function of x. However, what we can do is if we restrict our attention to just a little piece of that graph, we can look, for instance, at this blue there it is, at this blue section of the graph, and I can ask for that section the same questions we ask for functions. Does it go up? Does it go down? Does it have a minimum? What is the slope of the tangent line? And so on and so on. Of course, if we're going to ask all these questions, the way we're going to answer those questions is by using implicit differentiation. So again, something we've seen before, but from a different angle. So we're arriving at these curves as level curves of a two-variable function. The other issue which we're going to look at right now is related to derivatives. Now, I've just said that a two-variable function has two inputs, but what we can do is we can pretend that one of those two inputs is a constant. So what we're going to do, what we can do is say, all right, z is a function of x and y. Pretend that x is a constant, then this becomes just z is a function of y. And so what we can do is we can think of this function as simply a function of one variable, as we've done so far. Okay? In that case, we can take the derivative of that function with respect to the one variable that we're still considering as a variable. And what we're going to call this is a partial derivative. It's not a full derivative because we're ignoring one of the two variables, but it is a partial derivative. Now, how do we denote a partial derivative? Well, we can denote it the same way that we did before. So we would say, for instance, that if we're holding y constant, and if we're thinking of x as the variable, then we can think of the derivative of f that is a function of x and y with respect to x only. However, it turns out that these partial derivatives are best, or it's better to separate them clearly from the usual derivatives in many situations. Not always, but in many situations. And so mathematicians have invented a whole new symbol for that. And that's something that looks like this. So some people pronounce that still as df by dx. Some other people want to show off. They will pronounce it as del f as del x, because that symbol is also called del. And notice that it is not a D, nor is it the Greek letter delta. The Greek letter delta is written differently. So it's a special symbol created just for partial derivatives. Now, sometimes this symbol is a little bit too much, or the fraction notation, the Leibniz notation is really too cumbersome, so we may want to have something shorter, sort of like the f prime notation that we're using. Well, in that case, we're going to use still something like that, but instead of f prime, which would not tell us which prime we're considering, we use f with the subscript of x. Okay, so f sub x will mean the derivative of f with respect to x only, keeping y as constant. Of course, we can look at the other side of the coin. Take the derivative of f with respect to y. So this time we're going to keep x. We're going to consider x as a constant. Same symbol, del f by del y, and similar notation, f sub y. Okay. So once you know this, then you can compute partial derivatives already. You just have to use the regular rules of differentiation. Just keep one of the two variables as constant, consider as a constant, and compute the derivative normally. Okay. Now there is, however, some interesting things that can happen with functions of two variables, and we're going to be looking at some of them next time. But as I said, the more interesting, the more intriguing, the more challenging ones will really be looked at next year. So this is just a very basic introduction. As you can see, nothing too complicated, nothing too new, just more tools or more functions, more toys with which to play with derivatives and so on. And we're going to see in class how that playing is done. And again, next time we're going to see some other new properties.